Welcome again to the second lesson about kinetics. So in this lesson, we will be talking about the rate of reaction and how it is represented mathematically. And also we will be looking at the rate equation and understand what's meant by rate constant and reaction order. Okay, so just to recap on the lesson from last time. So the factors affecting the rate of chemical reaction, that these are the temperature, catalyst concentration, surface area, and pressure if the reaction is happening in the gaseous state. Now, this is basically all based on the collision theory, and the collision theory mainly is telling you that if there is an effective collision, this will lead to a reaction to happen, products to be formed. And if the collision is not effective, it's not successful, then the reactants will not form that reaction. Okay, so here I would encourage you to go ahead and do this activity. This is basically a simulation about the factors affecting the rate of chemical reaction. And this group activity is taking place in the class. Okay, so rate of reaction. If you remember last time when we spoke about rate of reaction, we said rate means speed. And when we speak about reaction, obviously we're not speaking about the distance, but we're speaking about concentration. So the rate of chemical reaction, it can be looked at from two points of view. It's whether you are looking at how the rate of the chemical reaction or how the reactant decrease in their concentration over a period of time, or how the product are increasing in their concentration over a period of time. So if we want to write what we've just said in words, so we can say the rate is directly proportional to the concentration. Fine. So since the rate is directly proportional to the concentration, then we can remove this proportionality sign. So if you were to remove this proportionality sign, you need to say rate equals to a constant, let's call it K, and this is basically the concentration. Now, this here, this equals to K, equals and K, are a replacement for the proportionality sign. Fine. So up to now, that's fine. This equation here, we call it rate equation. Rate equation. Fine. Let's move to the next slide. So basically, if we have this equation here, A and B, the rate of this chemical reaction is the concentration of these reactants, A, B. And as you can see here, it's raised to the power M and raised to the power N. Now, notice that in this chemical reaction in front of you, the coefficients are given small letters of A and B. So obviously this M and N are different to A and B. Fine. And if we were to look at the rate of the chemical reaction from the perspective of the products, so these products then will be looked at as being reactant, obviously, and the rate will equal to the K, C, D, and they'll be raised to, again, the small m and n. So the m and n here are different to A and B if we're talking about the concentration of reactant, or on the other hand, they are also different to the C and D. So what are these things here called M and N? M and N are basically exponents, and these are called reaction order. And we can only determine them by experiment. Fine. So far what we have learned, we've learned that this is how we write the chemical rate equation. So the rate equation equals to K times the concentration of reactants, and this is raised to power M and N. And later on, we will know how to calculate M, and N. Okay, so if we were to write the rate equation of this reaction, so K is a concentration of this and this. And for this reaction, the K here is a concentration of this and this. And K here is a concentration of this and this. Now, I want you to pay attention here. Now, didn't I say that the rate of chemical reaction will equal to the rate equals to, let's take the second one, NO and CO. And this is raised to the power M and N. And we said N and M, they are basically determined experimentally. So M here, when we determined it, we found it to equal to 2. So that's why we wrote 2 here. This N here, when we determined it experimentally, we found it to equal to 0. And anything raised to the power 0 is 1. That's why we didn't write it. Fine. Now, in this case here, in the lower case, as you can see, the H2O and NO2, when we wrote the chemical equation, we found that it's H2, it's not raised to the power 2, it's nothing to do with this 2. So that's why it's raised to the power 1, because this one, we determined it experimentally, and we call this the reaction order, and we'll learn about it in a minute. Now, this 2 here, it happened to be the same as this coefficient, but actually, it's nothing to do with this coefficient. It is basically a value that's been determined experimentally. Now, in this chemical reaction, as you can see, here you have this species here, and the second species is supposed to be this species raised to the power 1, raised to the power 1, and this raised to the power 2. If you see here, the coefficient, nothing to do with this, and the coefficient of the first one and the last one, first one is 1. Yeah, it happened, they're the same. And the last one, here it's 2 and here it's 1. So this is just to show you that these coefficients or these factors, the exponents, they are determined experimentally and they are nothing to do with the balance equation in front of you. Okay, the next thing we need to be looking at here is the reaction order. So what is then reaction order? The reaction order with respect to a particular reactant is the power to which concentration of reactant is raised in the rate equation. So this is the definition of the reaction order. Now, the reaction order can be any number, starting from 0, 0.1, half, but generally in this level, we will be speaking strictly about 0, 1, and 2. Fine, but don't be surprised if you looked somewhere else and you found the reaction order to be 0.5, for example. Okay, now this M and N are reaction orders, fine? So the overall reaction order of the chemical reaction is the summation of these two. So for example, if this is 1 and this is 1, so the overall reaction order of this chemical reaction is 2. But when we say this one, the M here is 1, so that means the reaction order in relation to A is 1. And if this part here is 2, if the N equals to 2, we'll say that the reaction order in relation to B is 2. Okay, so we need to make this differentiation. Again, if the M value is 2, for example, so we'll say the reaction order of this chemical reaction in relation to the reactant A is 2. If this is 1, the reaction order of this reaction in relation to B reactant is 1. The overall reaction is the 2 and 1, which is 3. Okay, so this is how to write the rate equation and the value of X and Y, or M and N. We will determine it from the calculations now. Okay, so if I look at this activity here, now we have 3 cases. we have the concentration. As you can see, it is doubling, and we have the initial rate. So when the concentration was 0.1, the initial rate was this number, and then when we doubled it, it was doubled, and when we doubled that, also it was doubled. Now, in this case, as you can see, when we double the concentration, here it increased by 4 times, and when we double the concentration, here it increased by 4 times. Here, in this case, when we doubled the concentration, it remained constant, and when we doubled the concentration again, here it remained constant. So what's the story then? What are we trying to say? We're trying to say here that the order of the chemical reaction can be obtained from this experimental data. So let's see how. Now, the way you can do this is see how much the change in concentration is related to the initial rate. So when we double the concentration here is basically doubled. So if you take the ratio, and this is how you calculate it, if you take the ratio 0.2 divided by 0.1, and the ratio here is you take ratio between two consecutive rows, and you take the ratio here between the same rates, so it's 0.03, 0.015. So this here, it will be 2, and here it will be 2. So here you will want to know how much the concentration affected the rate of the chemical reaction, this change in concentration. So the change in concentration, X here, or you can call it M, or you can call it N. Here, basically, it's raised to the power 1. Here, it's raised to the power 1. So X, in other words, if you want this number to equal this number, this X here has to be 1. X here equals to 1. Fine. Now, let's look at the second case. The second case is when we have 0.2 divided by 0.2 equals to, this is 0.6, 0.06, and 0.015. So this is 2 raised to the power, call it anything, let's call it M, equals to 4. So you want to see how much the change in concentration has basically affected the rate of the chemical reaction. So here in this case, this M must equal to 2, because 2 to the power of 2 equals to 4. So M here equals to 2. So this order reaction, the order for this reaction here is 1, or you can call it first order, and the M here is 2, and you can call it second order. Now, the last case is when you have 0.2 divided by 0.1, and here you have 0.015 divided by 0.015. Now here you have 2 raised to the power x equals to 1. So how can you get the value of 1 here? Basically, this x has to equal to 0, because anything raised to the power 0 is 1. And therefore, basically, there is no effect on the change in concentration in this chemical reaction on the rate of the chemical reaction. If you change the concentration here, the rate will not be affected. Okay? So this is basically what's meant by the order of the chemical reaction and how to determine it from experimental data and from mathematical calculations. Okay, so if we take an example on this, here we were told that this chemical reaction, the data shows doubled. Okay, so this is an answered example. Let's take another example here. And this is these are the cases or the answers of the cases above. Fine. Okay, now you have in this chemical equation, you are given the rate law or rate equation, and it tells you that rate equals to a constant, and this constant is called rate constant. And here the concentration of NO and concentration of H2. Now, this two, it happened to be same as this, but it's nothing to do with it. This value is determined experimentally, and this value, as you can see, it's different to this value. Here, there is one. You don't write the one. There is one here, and there's two here. So these coefficients are nothing to do with the reaction order. That is how much the change in concentration affects the rate of chemical reaction. So this chemical reaction is second order in relation to NO. And this chemical reaction is first order in relation to H2. And this chemical reaction is third order in relation to both of them. If you want to take the overall, so this is 2 plus 1, that is 3. Fine. If we look at the order of reaction, so if we have these graphs, basically we can deduce what type of order we are looking at. So in other words, if you do an experiment, if you change the concentration over time and you get inverse relationship, in an inverse relationship like this one, or a parabolic relation like this one, or like this one, then you can deduce which one is what sort of order. So if you have an inverse relation like this one, it will be a zero order. And if you have a relation similar to the one in blue, it will be first order. And if this very steep as compared to the blue one, then we can call it second order. Okay, so this shape here, it summarizes three of them. This is important for the exam. You should make sure that you know it. Okay. We will take this activity and solve it together. Okay, so now we have this equation. These are solved examples, so I would invite you not to look at them and try to solve them by yourselves. Let's look at this. Fine. Now you have a chemical reaction like this. You are given some experimental data, and you are told two things. Write the rate law of reaction, and then determine the rate constant for this reaction. Okay, so to start with, what I would say that I have the R, the rate law here, equals to a constant that I don't know, times the NO2 times the CO. And here there is M and there is N. And I don't know the M and N. That's what I'll calculate from. So in order to determine the rate law, I must determine this and this. Okay. So to start with, I need to determine what is the value of M. Now to determine the value of M, and here we're talking about the NO2, the value here, fine, has to be changeable. So the concentration must change between two rows, but the other reactant must be constant. So you can't basically use these two rows, this and this, you can't use them to determine the M of the NO2. Why is that? Because here the concentration is changing, here the concentration is changing. But you can use the first and second row. Why? Because the second reactant is constant in this case. So if we say 0.2 and divided by 0.1 to the power of M equals to the 0, 0, 8, 2, and here 0.0021. Fine. So basically here you have 2 equals 2 and raised to the power m equals to 2. Fine. So sorry, equals to 4. So here basically this m. So this m must equal to 2 in order to make the equation to be correct. So the chemical reaction in relation to NO2 is second order. So this m here, we can replace it by second order. Fine. The next thing is I want to determine the n value. The n value, I have to choose 2 rows where the concentration of the NO2 is fixed. So these are the 2 rows where the concentration of NO2 is fixed, where I can determine the concentration of CO. So these are the second and the third. So let's see. Here we have 0.2 divided by 0.1 equals to 0.0082 by almost same number. So here we have 2 raised to the power x equals to 1. In order to make x here, or to call it, we'll call it n. In order to find n must equal to 0. So this will equal to 0. So the rate equation, the R here, equals to K times the NO2 raised to the power 2, because we found m to be. And then the other one, we don't need to write it because it will be raised to the power 0, and power 0 equals to 1. Okay, now what do I need to do next? Next, basically, this is the first requirement. The second requirement is determine the rate constant. They want this rate constant. In order to do this, you can choose any of these rows and apply in the equation directly. So the initial rate, let's take the first one, for example. The initial rate here is 0.0021 equals to K. And here the concentration of NO, it was 0.1. Don't forget that the 0.1 here is raised to the power 2. Fine. Okay, so the 0.00 and here, so if we calculate that, that will be 0.21 divided by 0.1 divided by 0.1. That is 0.22. 21, sorry. So K equals to 0.21. Now, you need basically also to find the units for this. The rate has a unit of what? The rate has a unit of mole decimeter cube per second. Because as we know, the rate, I'll write it here, the rate concentration over time. So the concentration is molarity. Molarity is mole decimeter cube per second. And then you divided that by concentration. But the concentration here is raised to the power 2. That means it's mole decimeter cube, and minus, of course, and then again mole decimeter cube. So this small decimeter cube will cancel out the small decimeter cube, and therefore the final answer will be S minus 1 mole minus 1 decimeter minus 1 plus 3. Okay, and this is, of course, this unit belongs to this number. Fine. So this is a lesson to be learned, that each rate equation has the k in it has its own unit, and you need to deduce the unit based on the rate equation of your reaction. The next thing, basically, we have more examples similar to what we have learned. So in the class, we will basically learn more examples and take more exercise about that. I hope that was beneficial to you, and see you soon.